This is a year 2020 paper 2 question A5. So in this question, it shows table 5.1 shows some oxides element from group 1 to, let me see, group 1. Okay, this you got to change this thing. This is group 1, group 2, and it's group 13, 14, 15, and 16, and so on. They no longer use this Roman numeric. Okay, in case you don't know what is this, it is changed to, like, for example, group 1, group 2, 13, 14, 15, 16. Now down here they say that these are giant lattice and these are simple molecules, from simple molecules. Now the giant lattice is up to silicon dioxide. Of course, carbon dioxide is a small molecule, but silicon dioxide is actually a giant structure. Okay, first question. Carbon and silicons are elements in the group 14 of the periodic table. The oxides have very different melting points. So they are both in group 14. Somehow the melting points are very different. So this one is quite a standard question in the chapter chemical bonding you need to study. Okay, why are the oxides having very different melting point? Explain how and why melting point of carbon dioxide and silicon dioxide are so different. First of all, they did not say who is high, who is low, right? They just say different. So in your question, you must be very specific to mention that silicon dioxide is high, all right, and this one is low, all right. So carbon dioxide exists as a simple molecular structure. Please memorize that properly. Silicon dioxide exists as a giant covalent structure. Try not to use the word giant molecular structure. Alright, because this down here, silicon dioxide is actually not a molecule, but more of a giant structure where all the atoms are joined by strong covalent bonds. So let's just say as a giant covalent structure. Now the melting point of carbon dioxide is low, in fact very low, because a small amount of energy is required to overcome weak intermolecular force attraction between the molecules in the carbon dioxide. Take note of the word overcome weak intermolecular force. Next one, melting point of silicon dioxide is high. It's very high, in fact, very, very high, more than 3000 degree, about 3000 maybe. Large amount of energy is needed to break the strong covalent bonds. Now, do you see a difference? Intermolecular force, weak intermolecular force, strong covalent bond. That is contrast. And then if its intermolecular force is overcome, but strong covalent bond, covalent is break between the atoms throughout the giant covalent structure. You don't break one bond, two bond, break into half. In order to melt, you must break all the atoms, atomic bonds, the bonds between the atoms throughout the entire giant structure. So need a lot of energy. So this question is very important. I put star here. Please memorize the answer properly. From the table, give one acidic oxide and one basic oxide. Now, obviously, you choose things that you're very familiar. Sulfur dioxide, acid rain, right? Nitrogen dioxide, acid rain. If you cannot remember the rest, at least remember these two lah, please. Acid rain. So they must be acidic. And of course, all the group 1 are strong. They're strongly basic. They're alkaline. If dissolved in water, they form alkali. Like for example, lithium hydroxide, sodium hydroxide. And magnesium, of course, is a typical basic oxide. Now, I highlight down here to show you there are 3 different kinds. Okay, down here is basically lithium, sodium, magnesium is basic oxide. The green color here is actually amphoteric oxide. But according to syllabus, you just need to know things like aluminum oxide, zinc oxide, and lead oxide. They are amphoteric oxide. B2O3 or BeO not necessarily remember. Alright? And of course, you don't go anyhow choose it and say that this is the basic oxide. Choose something you know. And now here, oxygen is neutral, but the rest are actually acidic oxide. Alright? Now, so I will choose like acidic NO2, SO2. Even CO2 is acidic. You must remember that CO2 causes the rainwater to be slightly acidic, and rainwater pH is about 5.5 to 6.5. Please don't forget that. Rainwater, carbon dioxide in rainwater causes pH to drop to about 5.5 to 6.5, slightly acidic. Universal indicator yellow in color. Now, if it's sulfur dioxide and nitrogen dioxide, then the universal indicator will turn to orange or red. Alright, pH lower than 4. Alright, so you did not learn BeO or B2O3 with, even though they are amphoteric. So you did not learn them, so you should choose only the confident ones like group 1 stuff that is alkaline or basic. Okay, draw a dot and cross diagram to show the bonding in MgO and O2. Now, sometimes they ask you to draw the bonding and they ask you to explain why MgO has high melting point, O2 is very low melting boiling point. But down here, just drawing. So MgO is ionic bonding. Each Mg give out 2 electrons. Each oxygen receives 2 electrons. When you draw the diagram, remember draw 8 electrons in outer shell of magnesium. Magnesium Mg has 282. After giving away 2, what you draw is the inner shell 8. Now oxygen has 2 6. And oxide means you receive 2 electrons. That's why it's a 2 minus on top. And these 2 electrons received cannot be paired together. Alright, you don't go and draw like this. Look carefully. Dot, 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 dot. And then draw the pair of cross together. Then you are wrong. Now just imagine you remove the 2 cross that you just received. Then this was the structure that was correct before the oxygen received electron. Because you need to pair. And then but you need to fill up all the 4 corners before you start pairing. Alright, so this is the diagram MgO and this is oxygen. How many you need to become stable is how many you share. So someone asked me whether do I need to use different symbol to represent oxygen. In this case, not necessary. Same element can use same symbol. But of course, in this case, magnesium oxygen, right? You don't get use cross for magnesium, cross for oxygen. No, please, magnesium oxygen are different element. They must use different symbol. So in this case, why do I use different symbol? Because I want students you all to know that this cross contributed by the atom on the left, the dot contributed by the atoms on the right. So it's 2 pair electron like that. Alright. Now, if you need to do drawing, you use different symbol. First, of course, we try to use a cross, which is easier to draw. And then second symbol you can use is a dot. Third symbol, it can be a white circle. And the fourth symbol can be a white circle with a cross inside. So these are 4 symbols you can use to draw the dot and cross diagram. So when you have multiple elements and multiple atoms of certain element, you don't need to use different representation for different atoms. Just make sure that same element, just use the same symbol because you don't have enough to go around. Alright? Now, discuss the difference between the way the bonds are formed in MgO and O2. How are they formed? Instead of talking about a property which you can regurgitate, now this slightly more difficult question, differences between the way the bonds are formed. So first of all, in MgO, each magnesium loses 2 electrons, 2 oxygen atoms, so they can form Mg2+. And each oxygen gains 2 electrons from magnesium to form O2-, forming the strong electrostatic force attraction between the ions, between the oppositely charged ion. Okay, let me just add in between the oppositely charged ion. Okay, they are oppositely charged ions that hold them together, and therefore this is how bond is formed. So we first talk about the electron transfer, forming oppositely charged ion, and then the attraction between opposite charged ion is called electrostatic force, and this one actually is the bond that is formed between magnesium and oxide. Next part, oxygen, O2. In oxygen, O2, how come I can write O2 here? Because the question here give me O2. So in order to, instead of writing the word oxygen, I want to emphasize that, hey, this is the oxygen O2 I'm talking about. Likewise for MgO. Other than that, we try not to write a formula to represent the chemical, rather write chemical name rather than formula. But in this case, we want to actually quote this and this. That's why we have MgO and O2. So quote the data. So down here in O2, which is the oxygen molecule, 2 oxygen atoms share 4 electrons to form strong covalent bond. There you are. Yeah, describing what you draw actually. And this strong covalent bond actually hold the atom together. Between the atoms, hold them together within the molecule. So this is actually forming of the covalent molecule O2. Simple covalent molecule.